Enthalpy diagrams are fairly simple. They can be confusing at first, but once you learn how to read them, it's pretty straightforward. So they're graphs, and on the y-axis we have heat. It's usually some sort of arbitrary units. Sometimes it's in kilojoules, sometimes no units are given to you. On the x-axis, it typically says reaction coordinate, which is pretty non-descriptive. Another term for it is the course of the reaction, as we go from the beginning of the reaction to the end of the reaction. An example of an enthalpy level diagram might be one that looks like this. So we start off at this point here, and this point here where we start off is when we have reactants present. Then it goes through some sort of path and ends up at the end where we have products present. In an enthalpy diagram, whatever is lower on the graph, that is at a lower energy, is said to be more stable. And if you think of it like a ladder, it's pretty logical. If you're low on the ladder, you're in a more stable position than if you're high on the ladder. So in this type of reaction, we have the products being more stable than the reactants. If I'm reading this graph, when we start off the reaction, we have to put some amount of energy in. And we put energy into it, and then as it's going down the hill, we get energy back. In this type of reaction, we get more energy out than we put in. If I want to attach numbers to it, suppose we have a value where the products are of something like 50, and where the reactants are, we have something like 160 units, probably kilojoules. Then over the course of the reaction, we start at 160 and we end up at 50. So going from 160 to 50 is a decrease of 110. And so negative 110, that is the delta H of the reaction. Overall, the change in energy from the beginning to the end, which means this graph that we drew here is an exothermic reaction because it releases more energy than it puts in. If I want to contrast this with an endothermic reaction, let's take a look at what that curve would look like. The axes are still heat and reaction coordinate. The difference here is we're going to end up at a higher position than we started. So as we proceed from the reactants to the products, we're going to put in more energy than we get back out. Let's attach some values to this. I'm going to make them somewhat, I'm obviously just making them up. Suppose this started at 110 and we finish at 250. Going from 110 to 250 is a change in heat of positive 140. And that positive 140 is consistent with this being an endothermic reaction. Remember, negative delta H is for exo and positive delta H is for endo. What about in this case, which is more stable, the reactants or the products? Well, for an endothermic reaction, because the reactants are lower on the curve, we're going to say that the reactants are more stable than the products. Another thing that we can infer from an enthalpy level diagram is what the activation energy is of a reaction. Activation energy is the amount of energy we need to put in to get the reaction going. So on this endothermic curve, starting down here and finishing up here is how much energy we have to put in. I'm going to draw that with an orangish arrow here. So going from the beginning up to the top of the curve, that is E sub A, which is known as the activation energy. From the beginning to the top. Drawing it on my exothermic curve, it's still from the beginning up to the top. That would be my activation energy.